We're live. Hello, everyone. And we are live. Hello, everyone. Welcome back to AST 111, office hours for 10,000. So I'm Frank. I'm the instructor of the course, and we'll be talking a little bit about some extra material today, since we didn't get a whole lot of questions on the discussion board. If you want, you can post some questions while we go, and I'll see if I can loop back to it and answer any questions. So let me check. Let's see if we got anything before we get rolling. There's the course discussion. Any new questions? No new questions. Okay, we'll go. Very good. So one of the objects that we don't talk a lot about in this course is the central object, the sun. So we talk a lot about how the solar system is made. We talk about the planets, interiors, Jovians, comets, asteroids, icy ones. But we don't actually talk a whole lot about the central gravitational object that is emitting all kinds of energy. So I want to cover a little bit about the sun today in a roughly 30-minute module. So let's go ahead and begin. And while I'm going, you can post any questions you want on our discussion board, and we'll take a look at them when we're done. Okay. Let's do it. So let's see, screen share. Screen share. And I will share the keynote. All right, I am assuming that we are showing the screenshot, so I will just begin. So all cannot live on the piazza, but everyone may enjoy the sun. The Italian proverb, and I love the color. And if you look closely at the picture here, there's some agelessness in the picture as we go. All righty, so here we go. So we're going to take a journey to the center of the sun and back. Currently, we have the Parker Solar Probe up and going. It is now in orbit to the sun, and its mission is to touch the sun, or at least touch the outer layers of the sun. And this is a first, and so we're going to get our first experimental evidence for conditions in the outer layers of the sun, which we will come to shortly. So that's the Parker Solar Probe. But we're going to start on Earth, and we're going to take a journey to that center and back. So as we begin our journey on Earth, the sun looks like a ball of glowing gas, and pretty much that's what it is. It's a hot ball of gas. It's glowing. It's just like a thermal radiator to a 0th order approximation that we know about thermal radiators from our third week in AST 111. So the total power output of the sun, so how many joules per second come out, which we measure in watts in the SI system. That's called its luminosity, so we'll call the sun's luminosity. And it's a pretty whopping about 4 times 10 to the 26 watts. That's 4 times 10 to the 26 joules every second that comes out of that. And so if we could store just 1 second of the sun's total luminosity, it would meet current human energy needs for about 500,000 years or so. So although the sun is a fairly garden variety star, it puts out a prodigious amount of energy. And of course, the Earth itself only intercepts a tiny fraction of the sun's total energy output. In fact, I believe we've had a couple of assignment questions on this. The Earth, every square meter of Earth intercepts about 1,000 watts. So we get about 1,000 watts per square meter, so-called solar constant. And that's to be compared to the 10 to the 26 watts that comes out. And so the sun disperses in all directions. This image here is a lovely image of the sun in white light. on the left, and then with an H alpha filter. So that H alpha filter uses blocks out most of the light, except light in a very narrow band, which we call H alpha. And of course, you can see all kinds of phenomena here on the surface of the sun. We got some prominent sunspots going on. We got sort of that boiling, roiling surface on the left. You can see some prominences on the left side as well, and we'll cover some of these as we go through the rest here. Okay. So most of the energy that we receive from the sun is in the form of visible light. That's why our eyes see invisible light. We've gravitated toward the sun, where the energy that we get is maximized. But once we leave the protective blanket of Earth's atmosphere in our journey to the center, we're going to encounter other types of solar radiation, including ultraviolet and X-rays. And the image here is an example of what the sun looks like in particular X-ray bands. The colors here correspond to different X-ray energies. Just like optical light comes in different energies, and so we see those as purple to red in a spectrum, and you sort of do the same thing here with X-rays as you color according to the energy or according to the wavelength. And so we get sort of this modeled pizza with some hot gases coming out of what look like holes, which is exactly right, of the surface of the sun. This is from a NASA satellite known as NuSTAR. That one's currently in orbit and exploring our solar system and the universe in X-rays. So as we head out toward the sun in our journey, we're going to need some substantial shielding to prevent us from those high energy photons and other particles. Otherwise, we're going to get burned pretty good from those high energy forms of light. I just kind of like this picture. I think it nicely encapsulates several millennia of travel. So we start off with the old clipper ships, wind-powered sails there in the front, and in the background is an approximation of where we are currently, where we blast off shuttles. That is the space shuttle there, blasting off into near-Earth orbit. And then, of course, we have our science fiction, which largely dictates that we shall be bustling around other solar systems and part of the galaxy, in, for example, the Starship Enterprise there in the upper left. So I kind of find it always fun that our art sort of guides where we shall go with the technology as we develop it. All right, so we've got some shielding. We are headed to the sun. And as we head to the sun, we're going to take that light, and as we learned in week 3 of this class, we're going to take that light and we're going to bust it up into its component colors. This is called spectroscopy. This is a spectra of the sun. You see that continuous spectrum from purple to red, and interspersed on that, as we have learned, are the absorption lines, right? This is where individual atoms are absorbing particular frequencies of light, various wavelengths of light as it goes through, and this produces a dark band, a blotch in the sun. And so when you do, this is the fingerprint of the sun. And so when you analyze this fingerprint, you find that the sun is made of about, the surface layers of the sun are made of about 70% hydrogen or so, about 28% helium, that's 98%, and then 2% of everything else, which is all the good stuff that we're made out of, things like carbon and oxygen and nitrogen and iron and silicon and sulfur and gold and all that stuff. It's present in the atmosphere of the sun, but it comprises about 2% of the total. And in fact, helium, which is the second dominant component in the sun, is how we discovered helium. Because helium is not present in great amounts on Earth. It's lighter than air. It escapes. That's why we have helium balloons. And so it was the sun where we actually discovered the element of helium. And that's why helios is the Greek word for sun. And so helios, helium. And so helium is sort of named after the sun in itself. All right, so we know what the sun is made out of as we head out. And as we look through our telescope, we can see that the sun is seething, churning, burning ball of gas. But there's at least a few sunspots that are blotching its otherwise fairly uniform appearance as it moves across the surface. So the image there shows some sunspots over the course of about 5 days or so as they move through the northern latitudes in the sun. The bottom image shows the approximate size of the Earth. So these sunspots are huge. They're much larger than the size of the Earth. They're also blindingly bright. They only look dark against the brighter surface of the sun, the hotter surface of the sun. So sunspots are a little bit cooler, and hence they look darker, but they're just a little bit cooler. They in themselves are quite bright. And these images were taken with the NASA SOHO Explorer, I do believe. Yes, it's right there, NASA SOHO. So yeah, these were the looking at the sun before we actually sent a mission to the sun, the Parker probe, which we covered on the first slide a little bit. So I'm looking forward to the results that will come out of the Parker Solar Probe. So if we watch these sunspots, you'll notice, as we did in the last one, so you notice that the sunspots are sweeping across the surface of the sun. And what you find is that those sunspots that are near the solar equator circle the sun faster than the ones at higher latitudes. And this is how we tell that the sun is rotating. The sun is not rotating at a constant rate. It's not a solid ball. It's a gaseous ball. And so the solar equator takes about 25 days to rotate around, and we get that just from watching sunspots as they go around. They're kind of like clocks, if you like, for us. They're markers on the surface as it rotates around. Whereas by the time you get up to the poles, it takes about 35 days to rotate around. So we have a difference of about 10 days in the rotation period in the surface of the sun from the equator up to the poles. So we have a differentially rotating ball of gas. So as we continue toward the sun, we're going to notice the wind is getting larger and larger as we move toward the sun. And this is the solar wind. It's going to create a drag on our spaceship. So the solar wind is created by light, photons. Those photons carry energy, they carry momentum, and they alone can slow an object down. But there's also particles coming out from the sun. These particles are generally protons or hydrogen atoms that have been stripped of their electrons, so it just becomes the bare proton. There's also helium nuclei. So again, helium atoms with the outer electron stripped, so it's just the nuclei, 2 neutrons, 2 protons make up a helium nuclei. And of course, those electrons that are stripped off the atoms, they go around for the ride too. And so it's this combination of photons, protons, helium nuclei, and electrons that are constantly flowing out from the surface of the sun. The image here sort of gives a map of where we are headed as we head into the sun. We are somewhere approaching the sun. We're out near the solar wind. And we have the corona, which is where the Parker Solar Probe is going to be checking out. And then we have some of the various layers as we go through. We've got the chromosphere, we've got the photosphere. You'll see all kinds of solar weather at the front. You've got flares, you've got prominences, sunspots, granules. Eventually we'll get below the surface of the sun. We'll get into what's called the convective zone. Then deeper in, we will get to the radiative zone. And finally, at the center, we will touch the core, which is where the nuclear reactions that power the sun on long timescales are taking place. And then we'll journey back out from the core of the sun. So the solar wind has a deep impact on planets that orbit the sun, and presumably other planets that orbits their sun. Because if those planets have any sort of a spinning, conducting fluid in their cores, this sets up a magnetosphere, and it helps protect the planet from an otherwise biologically unfriendly solar wind. So the image on the right, Earth has a very active dynamo in the middle, sets up a comfortable magnetic field. So as that solar wind comes in, our magnetosphere blocks a lot of those high energy particles from coming in and sort of giving us a cocoon, a sheath against the solar wind. Mars had one that looked like the Earth on the right, but Mars is smaller. Mars cooled off, and once it cools off, then that liquid core becomes more solidified. The magnetic field goes away, and the solar wind can come in and get a lot closer, if not hit the surface directly. And so that's generally not a good thing for biological life as we know it. And so, yeah, Mars had a magnetosphere and lost it. And they shaped that solar wind as it goes out. So we're going to be about a million kilometers or so from the surface of the sun is when we enter a new layer of the sun, which is called the corona. And this is the tenuous uppermost layer of the sun's atmosphere. You can see the corona during a total solar eclipse. If you've never seen one, I highly encourage you to. There's one coming up in 2024 in the US. I saw the one in 2017. It was a lot more visceral experience than I had expected it to be. So it was way cool. So check it out. The next one, 2024, if you can, and you will see the corona once you get into totality. And that corona stands for the color sphere. And it is in the corona is actually pretty darn hot. The corona itself is about 1 million degrees, which is almost as hot as the center of the sun. So that's kind of weird, right? You've got the outer part, which is almost as hot as the part where you're producing nuclear reactions that power the core. But even though it's hot at 10 to the 6, we don't feel that heat very much. You don't get a lot of that energy because the density is so low. It's the very tenuous outer layers. And so although it's quite hot, the density is quite low. You don't transfer a whole bunch of heat. And it is the corona that emits most of the sun's X-rays. So as we go into the sun, each layer is going to emit certain types of energy. And the corona, it's the X-rays, and we'll see the other ones as we get in. It's kind of not unlike the Earth's atmosphere, where different layers in the atmosphere are going to absorb different types of energy as you go through, with the outer layers picking up most of the X-rays. Same thing here, outer layers are emitting the X-rays because it's the sun. So this image is a NASA image. Again, the colors are showing different temperatures here. And so you sort of get this blue-green pizza effect with white pepperoni pizza on it. And you get some of the outer parts of that color sphere of that corona. So farther in, the temperature is a ripe, toasty 10 to the 6. And as you go in a little bit, all of a sudden, the temperature is going to drop quite rapidly to about 10,000 degrees in what is called the chromosphere. And this is where the sun is going to emit most of its ultraviolet radiation. And then as we continue going in, we're going to meet the photosphere, which is what you see with your eye. This is where most of the visible light is emitted. So each layer emits different types of light. And so when you talk about the photosphere, this is the light sphere that you see in the optical. So the image here is a function of temperature, is a function of height. So on the outer part, where the height is the largest at about 3,000 kilometers above the photosphere, is where you have the corona. And then we transition into the chromosphere, where it's cooler but still hot, ultraviolet. And then finally, the temperature goes down some more until we enter the photosphere. So the photosphere is actually sort of the temperature minimum. It's the coolest at the photosphere, where most of the visible light is emitted. And as I mentioned, the chromosphere is the primary source of the sun's source of ultraviolet light. And I just like this artistic rose of the chromosphere, and you can see spicules and flowing patterns of magnetic fields going through there. It's a beautiful picture, rendered in pink of the sun's chromosphere. So as we head into that chromosphere, we're going to find that our compass, our GPS device, if you like, is going absolutely nuts as we go through the solar atmosphere, indicating that the solar weather through the corona and the chromosphere and the photosphere is largely driven and shaped by intense magnetic fields. So this is an example of a simulation near the surface of the sun. So the colors here are indicating the strength of the magnetic field, which itself is embedded in a turbulent, convective, roiling, boiling fluid. And so it's that interaction of the fluid with the magnetic field that gives sort of these structures to the magnetic field as we go through. Occasionally, as we head through the chromosphere into the photosphere, you're going to see huge magnetic storms occurring, and these huge magnetic storms shoot out all kinds of gases into space, and we call these different names depending on the type of energy that is spit out. So we have things like flares, prominences, granules, supergranules. Here in this image here, this is a NASA image, you can see several of that. You can see places where it appears to be a source of the magnetic field, a source of the hot gases. Those are sunspots. So those things in the middle, those are what the sunspots look like in the ultraviolet, in the chromosphere. And then you've got those loop structures on the outside. These will break. Those are magnetic field loops, and one of those magnetic field loops is when you get flares and prominences, and those loops go between sunspots. Sunspots are the anchors of the magnetic field. And at long last, after we've been through the corona and the chromosphere, we reach the visible light surface. This is the photosphere, where the temperature is fairly cool. It's about 6,000 K. And so this is an image of an airplane with a couple of sunspots moving across the sun in that visible light surface that we are also very familiar with. And as we slip below the temperature minimum of the photosphere, we find that our spaceship is tossed around by incredible turbulence convection. We see spouts of hot gas rising up and cooler gas cascading downwards. So we are in the convection zone, where energy is transported by moving material. This is something we covered in week 3. So one of the primary ways that nature moves energy from A to B is by convection. So it's hot on the bottom, cooler on the top. Hot stuff rises up, releases its energy, it cools off, the cold material goes back down to pick up another parcel of energy and move it from the bottom through the top. And so this is the roiling, boiling appearance of convection, which you see when you put a pot of water, for example, on the stove and heat it up. We've seen this picture before. This is our map. This is sort of where we are. We are now below the photosphere, and we are into the convection zone. And we see the photosphere above us. As we turn around and we look back, we can see that photosphere, and you realize that the photosphere is actually the top of the convection zone. And it is this convection that gives, when you look at the image of the sun, this appearance of a churning, boiling appearance. So this is an image of the sun from the vacuum powered telescope. It's centered on a sunspot there, so it's darker because it's a little bit cooler. But notice around that you see bright regions, which indicate material coming up. And then surrounding those bright regions and these granules, if you like, are dark regions. This is where the material has cooled. So the bubble has gone up, the bubble has burst, the energy is released, and then it's sliding back down toward the center of the sun in those darker regions. This is dynamic, right? Because it's a boiling, churning, convective pot of gas as it goes through. So this is how the sun moves energy in its outer layers, is through the convection zone. So as we keep on going toward the center, we get about a third of the way to the center or so, and we find that all that turbulence goes away, and we enter what is called the radiation zone, where energy, instead of being transported by material moving around, is able to be transported just by photons moving outward, the diffusion of photons as it goes on out. So here's another map of the sun. We've covered the corona, the chromosphere, the photosphere. We've gone through the turbulent convection zone, and we are in the radiative zone on our way to the core. And as we plunge down to that core, this is the center of the sun. Center of the sun is about 15 million Kelvin, and the density is about 100 times that of water. And we are at the heart of the energy producing region of the sun. This is where effectively 4 protons come together to make one helium nucleus. So it's the process of hydrogen burning. So we're going to burn hydrogen, 4 of them, to make one helium nucleus. And in the process of doing that, of converting those 4 protons into one helium, we get energy out. E equals mc squared. That's where it comes from. And so it is E equals mc squared, the burning of hydrogen, that powers stars like the sun at this phase of their life. And so this image here is focusing in on the core and the various other outer regions. Okay. So how do we know this stuff? I told you a story. It's a nice story. It's a great story. But how do we know any of it's true? So we know it's true because we can be innovative and do experiments on the material with the sun and the stuff leaving the sun, and in our probes of what's happening inside where we can't see. So one of those probes that we use is an analogy with earthquakes. The sun is not solid. It's a ball of gas. It shakes around like a bowl full of jello, and you can set up quakes, star quakes, vibrations of the sun, which are caused by pressure waves that propagate through the sun at all times. One of the primary modes of the sun is about a 5-minute period. So the sun, if you like, breathes on 5-minute time scales. And although we can't set up seismographs on the sun like we can on the Earth, we take a seismograph, we lay it down, and we can detect the earthquakes that go on the inside of the Earth. When that sun pulsates, when it oscillates, it changes the luminosity of the sun by a little bit. When it gets a little bit larger, it's a little bit dimmer. When it gets a little smaller, it's a little brighter. And so as it pulses back and forth, you can pick up these minute, small variations in the light output of the sun. And these are caused by the waves, and the certain types of waves that you get can then tell you about the interior of the sun, much exactly like earthquakes, when we detect them, can tell us about the interior parts of the Earth. And this topic has a name. It's called helioseismology. So you probably recognize seismology. That's the earthquake stuff, except since it's on the sun, it's helium, helioseismology. And we can probe beneath the photosphere. We can probe the structure of the convection zones and the radiative zones that are otherwise just invisible. And so in the sun, you set up standing waves, cavities, and they're going to be parts that are resonant. At the top part, these are the red regions on the left, and then there are parts that are going to be low. These are the blue regions on the left. You can set up this pattern of resonant waves within the sun, so the sun sort of oscillates, as you can see on the bottom there, between the red and the blue, and you can measure these oscillations through the light output. So this is one way that we can probe the interior of the sun, the outer layers, the radiation zone, the convection zone. Another way to probe the interior, which will probe the core of the sun, is to take a look at particles which stream from the center of the sun, which are known as neutrinos, little neutral ones. Because they're neutral, they don't interact too much, and they just fly right out of the sun. And if you are lucky enough to catch some of those neutrinos, they can tell you about the conditions of the sun. So as you read this sentence, there's about 10 to the 18th neutrinos from the sun that are going to zip through your body. Mostly they don't do anything because neutrinos rarely interact with anything, but rarely is not never. And so with patience and a large enough detector, you will catch a few of those. One of those detectors looks like this space alien thing shown in this picture here. This is the Borax-Eno detector. And all those tubes around it are photomultiplier tubes where you're looking to pick up the interaction of the light with the material inside. This is another neutrino detector. Note the boat there in the middle. Guys on a boat. And these are photomultiplier tubes, and these are all covered with very pure water. And so when when a neutrino comes in and interacts with the water, it sort of sets up, if you like, a sonic boom. As a few of those neutrinos interact with the light, and that sonic boom emits light, and that's what all those photomultiplier tubes pick up. So you're looking for little flashes of light, little fireflies inside Kamiokande neutrino detector. And then from the type of light, the energy of the light, you can back out the types of neutrinos, and then hence, in order to get those neutrinos, what the conditions in the center of the sun are. And so in that solar core, where the nuclear reactions are taking place, where you put 4 hydrogen together to make helium, this makes energy, and that energy is in the form of a high energy gamma ray photon. And as we mentioned, the density at the center of the sun is about 100 times that of water. And so one of these high energy photons only travels about a millimeter before it collides with something, usually an electron. And so that scatters the photon into a different direction, in a random direction. And so these photons that are produced in the center of the sun, unlike neutrinos, which just free stream out of the center of the core without interacting like anything, the photons diffuse out. They bounce around like a drunk person from one scattering event to the next scattering event. And along the way, each time it scatters with something, the photon loses a little bit of energy. It shares its energy with every scattering. And so these gamma ray photons, these high energy nuclear gamma ray photons, are gradually transformed into lower energy. And so one gamma ray photon produced at the center of the sun takes about 1 million years to go from the center of the sun to the outer layers of the sun. And that energy of a gamma ray photon has been converted into roughly about 1,500 or so photons of visible light. And it's those visible light photons, when they reach the photosphere, where light can escape from the interior of the sun, is what we see as the photosphere here on Earth. And this is a shot from the space station of NASA showing the outer layers of the Earth, absorbing that 1,000 watts per square meter from the sun's visible light. That's what I wanted to say about the sun, that central object in our solar system. And where is my screen sharing? So I stop my screen sharing and I come back. Yay, here I am. Okay. That was a 30-minute video module, a little bit longer than our usual ones. AST 111. So let me check, see if anybody has posted a question on our discussion board. And okay, I don't see any new questions. So we will call that one a day. This will be a 34-minute office hour on some new material. So let me get back to there. Very good. Okay. Feel free to post your questions on our discussion board. The end of the course is coming up. You will have a proctored final exam if you're taking this for credit coming up. You also have a design project coming up due. There's a thread discussing various things people have done for design projects over the years. Just about anything is fair game. It can be a little bit more on the artistic side. It can be a little bit more on the science side. Do try and touch some of the learning objectives of the course, which are listed in the syllabus as you do your design project. You don't have to share your design project, but it's great if you do. Get some comments from your colleagues and your classmates. I'll throw a comment on there too as well. So feel free to share your design projects as you go. And again, ask any questions of our discussion board, and that will do. Thank you very much, everyone. Bye-bye.